In this sample, we're going to determine how much work is done by air resistance without ever calculating the force exerted by air resistance. So this could be a useful use of the work-energy theorem when you don't know how to calculate the force due to air resistance, or it might be impossible to take the measurements. There's a way around that sometimes. So that's what this problem is about. So I'm on page 292. An adventurous parachutist of mass 70 kilograms drops from the top of Angel Falls in Venezuela. The waterfall is 979 meters high, and the parachutist deploys her chute after falling 295 meters, at which point her speed is 54 meters per second. During the 295-meter drop, what was the net work done on her, and what was the work done on her by the force of air resistance? So there's a lot of information in this problem that we do not need. So we need to read carefully, which is why I read the entire problem first once, sometimes twice, before I write anything down. Okay, so we know, because we're doing work kinetic energy theorem stuff, that we're going to need her mass. Okay, so her mass is 70 kilograms. Now, after reading it a couple times, you realize that the displacement, or the distance traveled in this problem, is the 295 meters. We don't care how tall the waterfall is. We're just talking about the point in between when she jumps and when she deploys her parachute. So that's 295 meters. Now, I'm kind of taking down to be positive in this, well, not kind of, I am in this problem. So that's going to come back later. I'm just going to make a note of that. All right. We can assume that her initial speed was 0 because she jumped off the top, and her final speed is 54.0 meters per second. So the questions, let's just be clear about the questions that we're asking. Net work done on the parachutist. Net work on. And then finally, the work done by air resistance. Okay, so a quick free body diagram is going to help, even though we're ignoring air resistance. We're not ignoring it in this problem. Once she jumps, there are two forces acting on her, gravity and air resistance. And I have not drawn those properly because this one should be longer, right? Because she is accelerating down. Okay, so in the scheme of things that I've decided here, this is going to be the positive direction and this is going to do the negative direction. So gravity is going to do positive work on her, and air resistance, is going to do negative work on her. So that's just kind of setting things up in our brain. So we know we're going to use the work energy theorem to solve this. And so we can write down that the net work done on her is equal to her change in kinetic energy, which is equal to, some stray marks here, which is equal to Kf minus Ki. And here we are again, Ki equals 0, because she's going to jump from rest, at least in the y direction. So we know that, that the net work done on her is equal to her final kinetic energy. So we can find her final kinetic energy. It's just 1/2 her mass times her final velocity squared, which is 1/2 times 70 kilograms times 54 meters per second, quantity squared, 1.02 times 10 to the 5th joules. Now, a joule is a pretty small unit of energy, so we're going to deal with a lot of big numbers. Don't worry about it. A joule is about the amount of energy you need to lift an apple above your head. So we're looking at tens of thousands, hundreds of thousands of joules. It's not all that much energy. So we know that since that's her final kinetic energy, that's the net work done on her. And that's it. We're done with part A. That's the work done on her. It's equal to her change in kinetic energy. Now, how much work is done by gravity? Work done by gravity. Okay, so remember our force is here, right? The work done by gravity, let's do it a different way. The net work is equal to the work done by gravity minus the work done by air resistance. Okay, so the work done by gravity is equal to the force of gravity times the distance she falls times cosine of theta. Well, remember the force of gravity is just mg, okay? The distance she falls is her 295 meters, and she's moving this way, okay? The angle between her displacement and the gravitational force is 0 degrees. The cosine of 0 degrees is 1. So the work done by gravity substituting is 2.02 times 10 to the 5 joules. That's the work done by gravity. So to find the work done by air resistance, I'm going to write this again. The net work is equal to the work done by gravity plus the work done by air resistance. And I want to come back here to this right here. I'm going to put that should be a plus. Okay. The net work is the work done by gravity and the work plus the work done by air resistance. If the work done by air resistance is negative, which is where we're going, so be it. Okay, so back here. To find the work done by air resistance, we have the net work minus work done by gravity. So give myself a little bit more room here. The work done by air resistance is the net work, which is 1.02 times 10 to the 5th joules, minus the work done by gravity, which is 2.02 times 10 to the 5th joules. So we get the work done by air resistance is negative 1.0 times 10 to the 5th joules. Okay, so that's the work done by air resistance. And you want to keep the negative there because what that means is, right, it means that air resistance is acting up. So on a problem, well, any problem where you're including work, you need to define the direction of displacement, and then any negative work would be effectively slowing it down. So that's how we can find the work done by air resistance, even though we don't know how to find that force. And now we could even divide out the distance and find the force exerted by air resistance. And if you were doing that in an experiment of some sort, you could use that to come up with a formula for air resistance. So that's a useful tool. It's a way for us to calculate something that we could not have calculated the normal way, right? Because if you're going to find the work done by air resistance, you'd have to do FD cosine theta, and the D is easy and the cosine theta is easy, but I don't know how to do this. So another illustration of how powerful the work energy theorem is when you can use it.